So the purpose of both of these standards is to determine the mechanical properties of plastic materials. On the left are images representing both types of tests, and on the right is an example of a stress-strain curve which shows some of the properties that can be measured from such tests, such as the tensile or bending modulus, which is the stiffness of the material, the yield point, which is the point at which a material is permanently deformed, and other properties such as the maximum strength the sample can withhold and the stress at break. In a tensile test, a sample is gripped on both ends and pulled until the sample fractures. In a bending test, the sample is placed on supports and pressed on by a punch until the sample fractures or a certain strain is reached. While tensile testing imparts only tensile forces, bending tests impart both tensile and compressive forces on the sample. So some materials will show very similar results between the two, while some materials may have very different tensile and bending properties. Not only will the method of testing result in different measurements, but specific details on how the test is performed, such as testing speed, sample dimensions, and hardware differences will result in different results. So when you're performing a test or maybe comparing data from tests performed at different facilities, it's important to be aware of how test conditions can affect the results. And that's really going to be the purpose of this presentation, to discuss those factors. And so there are different similar test standards for tensile and bending from other common standards organizations in addition to ASTM. And those are from ISO and JIS, as shown in this table. The standards largely align. However, there are some important differences in the details that require some special care. And they also actually have slightly different instrument requirements. I'll focus on the ASTM standards in this presentation, but provide some notes on the most important differences as well between ISO 527 and 178. This is a guide to give you some example recommendations, but it's not exhaustive. And of course, if you're performing any of these tests, you should refer directly to the standard and specific version that you're trying to follow. I'll begin first with ASTM D638, which is written for unreinforced and reinforced plastics. I'll point out that there are separate standards which are recommended for thin sheeting, films, and composites. And I'll also provide some comparison with ISO 527. ISO 527 is structured a little bit differently. It has a -1 version, which is general definitions for tensile testing. And then it has separate versions, -2 for molded and extruded plastics, -3 for sheeting, and -4 and 5 for composites. So to get a quick snapshot of these standards, this table provides the most important specifications to keep in mind when you're performing a tensile test. Going down the column on the left, we're going to have different recommended specimen dimensions, test force accuracy requirements, suggested test speeds, extensometer accuracy, and guidance for determining the elastic modulus. And then on the ASTM column, I've provided the specifications for the recommended sample. ASTM actually has 5 different standard types, which I'll talk about in the next slide. And these are the requirements for the type 1 recommended standard, which is a 3.2 millimeter thick specimen with a 50 millimeter gauge length. The specimen is recommended to be tested at 5 millimeters per minute, and the force accuracy measurements should conform to ASTM E4 Class 1 load cell accuracy, which is a requirement of plus or minus 1% force accuracy. And the ASTM E83 Class B2 accuracy, which I'll talk about as well in a little bit more detail. This specification for extensometer accuracy for elastic modulus is a focus of this presentation because there are differences, very specific differences in the accuracy requirements for extensometry. ISO, on the other hand, uses a 50 or 75 millimeter standard gauge length, although there are other options available as well for standard dimensions. And the required test speed is defined differently. It's defined as approximately 1% per minute strain, which comes out to 1 millimeter per minute for the standard samples, based off of grip-to-grip distance of approximately 100 millimeters. The load cell accuracy requirements for ISO are the same, however, they define extensometer accuracy differently, which results in a lower absolute accuracy requirement of plus or minus 1 micron. They also specify elastic modulus determination more strictly, saying it should be determined specifically from 0.05 to 0.25% strain. I'll review all of these requirements in a little bit more detail in the next few slides. As I mentioned, ASTM actually allows several different specimen shapes. As I mentioned, type 1 is the recommended standard type. However, there are alternatives for non-conventional or non-molded specimens where you can't control the dimensions as exactly. For instance, if a break does not occur in the parallel section of the grips, there's a type 2 specimen, which is available with a narrower width, so that there's more stress located within the gauge length. Then there's a type 3 specimen for specimens that can only be made in greater than a 7 millimeter thickness. Type 4 specimens for specimens that are only available below 4 millimeters in thickness. And type 5, which are special smaller dimension specimens for materials that may only be available in a limited quantity or perhaps have size restrictions, for instance, for testing inside the thermostatic chamber. The D638 also has provisions for tube and rod-shaped specimens. So with the test requirements in mind, we must ask, how does this affect our selection of test frame and instrumentation? For the test frame itself, you'll have to consider load cell accuracy, whether the test frame can achieve the test force required, and whether it can accurately control the test speed. In regards to load cell accuracy, as I mentioned, the ASTM standard has an accuracy requirement of 1%, which is generally the standard option from test frame suppliers. And you also want to confirm that the test forces are within the calibrated range of the load cell. Many test frame suppliers provide load cell calibration services so that you can confirm that the values that you're reading in test force are within the accuracy requirements. Shimadzu offers two lines of test frames, the AGXV and the AGSX, which are both standard compliant test machines for D638. The AGXV is our high-performance model with industry-leading specs such as high-speed sampling, high expandable input-output options, and very high rigidity. It can also handle all the challenges of a high rigidity sample. Typically a 10 kilonewton frame is enough for plastics. However, high-strength plastics may reach test forces above 20 kilonewtons for typical test samples. The AGSX is our other model. It's an all-around test frame with excellent specifications for the price. The next hardware consideration will be the grips that are used to grip the samples. Proper alignment and gripping is an important factor in tensile testing. Although D638 doesn't make any specific requirements, it does suggest that steps are taken to ensure there's proper alignment and sufficient gripping force so that the samples don't slip or break within the grip. There are two typical options for testing plastics. Pneumatic flat grips are popular for low gripping force applications because their gripping pressure can be adjusted and they actuate very quickly. And they also maintain their gripping force for samples that may thin during testing. Non-shift wedge grips, though, are generally the standard go-to grip because they've got large high-force gripping faces and the non-shift gripping action. They're available in a variety of grip face finishes, too, to accommodate different sample requirements. Back to extensometer specifications. An extensometer is an external device to the test frame itself, which directly measures the strain that's being applied to our plastic sample within the gauge length. ASTM D638 does have some provisions for performing a test with only based off of the movement of the crosshead, but if you are trying to directly measure modulus of elasticity, then it has higher accuracy requirements and requires the use of an extensometer. Extensometer accuracy is defined by a different standard, which is ASTM E83. and it provides different classes of extensometer accuracy. The absolute, each of these accuracy classes has both an absolute and a relative accuracy, which is going to depend on the actual gauge length that's being measured. For a 50 millimeter gauge length, for determining the modulus of elasticity, a class B2 extensometer is required, which results in an absolute accuracy requirement of to be within plus or minus 10 microns and a relative accuracy within 0.5%. The standard allows lower class accuracy extensometers if measurement is being taken beyond 20% or beyond the yield point, at which point an accuracy of only 10% is required. And in fact, after the yield point, it may be more appropriate to measure the extension based off of the crosshead movement. For instance, if necking is observed or strain is not occurring evenly throughout the gauge length. Many test frame software modules allow you to switch between the measurement from the extensometer to movement of the crosshead within the software. Comparing ISO and ASTM, there are some key differences within the extensometer accuracy requirements. The reason is that within ASTM D883, Class B2 extensometers are required to have an accuracy of plus or minus 5%, only down to a lower limit of 2% strain. So that means that for a 50 millimeter gauge length, the accuracy has to be within 10 microns for low strain measurements. ISO, on the other hand, has a lower fixed limit of 1 micron absolute accuracy, and they state that the error of strain for modulus calculations can be no greater than 1%. In other words, this results in a lower plus or minus 1 micron accuracy requirement for a 50 millimeter gauge length. This is an important thing to note, and one of the reasons that ISO suggests using larger gauge length specimens, because higher strain accuracy is achievable for larger gauge lengths. This is actually an inconsistency in the standard that suggested that the accuracy had to be below 1 micron for gauge lengths less than 50 millimeters, but this was corrected in the 2019 version of the standard and now has a defined minimum of 1 micron. So this is an important point to note that there are differences in the requirements between the two standards. So now with the extensometer requirements in mind, what options are there to comply with the standards? One of the most convenient and full-featured extensometers is an automatic extensometer such as the SIE 560, which is fully automated, capable up to 560 millimeters of travel. It complies with both ASTM and ISO requirements with an absolute accuracy of 1 micron below 0.2 millimeters of travel and a 0.5% relative accuracy above that. The gauge length can be set to any specified length with the use of a gauge length setting rod, and it can test up to break, and it has automated arms that grip and release the specimen at the touch of a button. Here's an example of elastic modulus determination of a PVC ASTM type 1 sample as tested with the SIE. You can see the high repeatability of the modulus results reported here of 5 replicates and reported with the standard deviation as required in the standard. On the right image, you can see the SIE in full. It mounts directly onto the test frame, so it's integrated with the test frame, and its controls are also integrated with the touch panel, which is attached to the test frame. There's also the option of fixed gauge length clip-on strain gauge-based extensometers, such as pictured here. These are also capable of achieving the accuracy requirements for D638 and ISO 527. They typically have easy one-handed attachment, but with the limitation is that you have to purchase them for a specific gauge length setting. And finally, there's the option of non-contact video extensometers, which are increasingly being used for strain measurement due to their versatility and convenience. Shimadzu makes the TRView X video extensometer, which is an imaging-based system that identifies and tracks gauge marks which are adhered to the surface of the material. It can measure both elongation and sample width for Poisson's ratio. It's very versatile, and since it does not contact the specimen, it's also usable with very fragile samples. And there's a 2-camera system available which can cover the entire range of strain that might be required for measurements. The operation is also completely integrated into the trapezium software so that recordings of the tests can be saved and played back in sync with the data. It does not have the absolute accuracy for the smallest gauge length samples with a minimum absolute accuracy of plus or minus 1.5 microns, and also it can be affected by certain testing environments, such as when samples tested within a thermal chamber, but it is a very versatile system. In the previous slide, I referred to measuring Poisson's ratio. Both standards mention some guidelines for determination of Poisson's ratio, although it's an optional and less common measurement. They differ slightly in the finer points. ASTM recommends applying a preload, and it defines slightly different guidelines for the calculation region, saying simply that it can be determined anywhere within the proportional limit, while the ISO standard suggests specifically determining above the 0.3% strain, since it is typically more difficult to get accurate strain at the low end. They both have the same extensometer accuracy requirements, which can be achieved, as I mentioned, with our video extensometer or with a contacting transverse extensometer, such as the one pictured. Next, on to ASTM D790 for the flexural properties of plastics and the complementary ISO standard 178. Once again, here's an overview of the essential specifications for running a bending test. They're going to come down to specimen dimensions, test force accuracy, test speed, deflection measurement device, how elastic modulus is determined, and some of the geometry of the hardware that's being used. For a bending test, the dimensions of the sample, such as thickness, width, and span, matter greatly because they will result in different effective strains and stresses on the sample, and also determine what crosshead displacement is required for a specific strain rate. So for the ASTM standard, the recommended sample dimension is a molded specimen that's 12.7 millimeters wide, 3.2 millimeters thick, and 127 millimeters long. Although there are provisions for different dimensions. And you'll notice that with changing specimen thickness, different widths are recommended. For ISO, the standard sample is a 4 millimeter specimen with a 10 millimeter length. Both tests require a test force accuracy of plus or minus 1%. In terms of test speed, the D790 recommends a 1% per minute strain rate. ISO defines it slightly differently. They provide a table of different test speeds and recommend a test speed nearest to 1% per minute. They both require deflection measurement devices, although ASTM D790 and ISO both provide some provisions for testing without a deflectometer. And then they differ actually quite a bit in terms of how elastic modulus can be measured. So I'll go into all of these details in the next few slides. So first off, ASTM D790 provides two different procedures, A and B. The default is procedure A, and it's recommended for elastic modulus determination at a strain rate of 1% per minute, plus or minus 10%. For materials with large deformations, a faster test speed of 10% per minute can be used. However, it's important to note that ASTM D790 claims that it's only valid up to 5% strain, at which point you can't be certain if the forces acting on the sample are purely bending forces or if other forces such as shear are acting on the sample. The ASTM method uses a formula to determine an exact test speed based on the specimen thickness and span. And you can see from the example that there are these bending tests are very slow. So based off of that calculation for the standard test specimen, the test speed is a crosshead movement of 1.27 millimeters per minute. It is ISO, on the other hand, provides a table of several standard test speeds and instructs you to choose the speed closest to 1% strain per minute. It also gives the option of testing at a higher strain rate if the modulus is not being determined. Don't be intimidated by the equation there, though. Within the trapezium software, it's very easy to simply set a straining rate controlled test so that you don't have to do all this calculation yourself. Next, to discuss some of the hardware. On the lower half of the slide, you see an image of a typical bending jig where you've got the two lower support blocks and an upper punch. This jig right here has a variable span so that the lower blocks can be moved, and also interchangeable supports. As I mentioned, the specimen thickness affects the span and width requirements of the sample. It also affects the radius of the supports and punches that should be used. This is important because it changes how force is concentrated on the specimen surface, with larger punches being used to reduce the compressive forces that are being localized on the surface of the sample. ASTM suggests a standard radius of 5 millimeters for the punch and supports, but it does provide alternative options. It does say that the punch radius should never be smaller than the specimen thickness itself or greater than 4 times the specimen thickness. ISO, in contrast, suggests a R5 punch, and either R2 or R5, that's a radius of 5 millimeters, supports depending on the specimen thickness. Both standards require deflection measurement accuracy of 1% and a distance between the supports of 16 times the sample thickness. Shimadzu's standard 3-point bending jig for plastics comes with both interchangeable supports R2 and R5 so that you can comply with both standards. Briefly, here are the calculations that are required by ASTM D790. They include flexural stress, flexural offset yield strength, which is the stress strain curve deviates by a given strain from the tangent of the elastic modulus, or the initial straight portion of the stress strain curve, flexural strain, and modulus of elasticity. ASTM D790 provides 3 different provisions for how modulus of elasticity is calculated. And here are the 3 different methods, and this is one of the main differences between the ASTM and the ISO standards. ASTM, as I mentioned, has 3 different methods. The tangent, which is just the tangent to the steepest initial straight portion of the curve. The secant, which is a line drawn through the origin and one other point on the curve. This is often used for materials that don't show an obvious initial linear region. And then there's a chord option, which is a line between 2 points. ISO, on the other hand, only provides provisions for a chord option and suggests that the calculation should be performed specifically from 0.05 to 0.25% strain, either as a strain line or as a linear regression on the data between the 2 points. So when you're looking at bending modulus values, you should be sure of how that modulus was calculated, and also be conscious of the general curve shape of the bending modulus. As I mentioned, they don't always have a very linear initial portion. Regardless of which method you choose to calculate modulus, it's good to know that all of these calculations are all available and easily settable within Shimadzu's trapezium software. You can see here it has a very convenient single-click list of options for calculating modulus, and in fact you can select multiple from the list. For instance, the chord, tangent, secant, the range that you want the calculation to be applied to, and other statistical information can all be really easily set within a method. In terms of test frame requirements, again, the primary requirement here is going to be in terms of test force accuracy, and both requirements are the same as for the tensile test in terms of a test force accuracy of plus or minus 1%. And both of our frames, again, are fully compliant with both standards, and the general properties are going to be the same. As for displacement measurement, both standards do recommend the use of a displacement gauge or a deflectometer. The best option for measuring bending displacement is a fixture like this, which is a 3-point bending jig which has a displacement gauge mounted directly through the bending base. This achieves a relative accuracy of plus or minus 1% and an absolute accuracy of 3 microns. You're also able to use arm-type deflectometers where they're mounted to the side of the jig. But displacement accuracy is important with bending tests, especially at higher force, more rigid samples, because the force of the test will actually cause deflection of the jig and of the bending crosshead itself. So using displacement measurements based purely off of crosshead movement will not be as accurate. If you do not have the ability to use a deflectometer, though, the ASTM standard does give an option for tests to be performed without one. However, it's recommended that a correction is made for that compliance of the test frame and fixture. It suggests that testing a high stiffness metal bar to measure the compliance of the system, and then using the equation below to remove that compliance from the data. Within Trapezium, there is a feature to perform this. It's called compliance correction, which makes the process very easy, where you can test the metal bar with a known modulus or with a modulus that's extremely high, and then referencing that compliance file to remove the compliance from future tests that are performed. So in summary, I hope that was a useful overview of some of the essential details to keep in mind when performing tensile and bending tests on plastics. Thank you all for your time, and we at Shimadzu are always available to answer any questions you may have or to help you out with testing solutions.
Thank you, William, for that fantastic presentation on ASTM D638 and D790. It was an excellent overview of those standards. We've had several questions come through, but I'd like to start with this question about ASTM D790. It says, you mentioned that different support diameters and spans can be used in ASTM D790. Can you explain when that would be needed and what effect it would have?
Yes, great question. So as I mentioned, the specimen thickness is going to affect the radius of the supports and punches. This is important because changing the diameter changes how much force is concentrated on the samples. And the standard is written in such a way that you can use different diameters and spans if required for different materials. So for instance, larger punches and supports will reduce the chance of compression failures under the compression nose. For instance, maybe with laminated materials that might have low compressive strength. Alternative spans may also be required to ensure that the failure only occurs due to bending moment. So larger spans may reduce those shear forces that may occur and cause premature failure. Wider spans require less force to achieve a given strain. And finally, also, I should mention that if you are changing spans, that will also, maybe change the length of sample that's required. So the standard states that a sample must be long enough to prevent the specimen from slipping through the supports as it's deformed. So sufficient overhang is required, and they recommend an overhang of at least 10% past the support spans.
Oh, wow, that's really interesting. So there's not just one reason for it, but many. But thank you for your explanation. That was very good explanation. This next question looks like it's a question about ASTM D638 and grips. So it says, what can we do to prevent samples breaking in the grips? So it looks like some people have trouble with their samples breaking in the grips as opposed to the narrowed section. Could you talk a little bit about that, William?
Yeah, this is a very common problem within tensile testing. Samples either breaking within the grips or outside the gauge length, and it's encountered with all types of different plastics, especially more brittle materials. And the main factors that affect this are going to be the gripping pressure that's used, the grip face surface, and the alignment of the sample within the grip, and also just the alignment of the two grips to each other. So you want to have, in terms of gripping force, you want to have the minimum gripping force required to prevent slipping, but not so much gripping that you may be damaging or weakening the samples within the grips. Many people have a tendency to over-tighten the grips, thinking that they really require the maximum gripping force, but that can actually damage the material. And I also mentioned that it may be necessary to change the dimensions of the sample if you consistently see this problem. So, for instance, increasing the size of the gripped ends or using a sample with a narrower gauge length. As many ASTM standards are written, they actually kind of allow you to make alterations to it as long as those alterations are well recorded and repeatable. So the other options or approaches are, for instance, techniques such as that are often applied with composite materials, is to reinforce the ends of the samples so that they do not break in the grips, such as adhering tabs to the ends of the materials samples. Or there's also a lot of different gripping face options that are available. Some people put sandpaper within the grips. As I mentioned, with our manual vice wedge grips, we've got different serration designs, diamond-coated surfaces that can all be tried to address this issue. And then finally, alignment. I didn't go into this in detail, but there are a few kind of tricks that can be used to make sure that the grips are in alignment and the sample is aligned within the grips. With dog bone samples, sometimes it's difficult to make sure that the samples are aligned kind of front to back, and so that takes some skill and procedures to ensure that those are aligned.
Oh wow, that's very interesting. So so you want to hold the specimen firmly, but not impart any additional stress onto the sample by the act of gripping it itself. That's really interesting. And even just the sample dimensions, changing those seems like we can achieve better results or prevent the samples from gripping. Thank you for that. Thank you for that explanation. So on to our next question. It is related to strain control, and it says, can you do strain control with these standards? So I'm assuming in this one we're talking about both standards.
Yes, that question is applicable to both standards. As I mentioned, within the bending testing, you actually are performing strain-controlled testing. Potentially, if you're using an extensometer, you can actually use the feedback from the extensometer to control the movement of the crosshead. This strain control testing has gotten increasing attention in the last few years, especially for plastics, because plastics are very sensitive to the rate of straining. And due to the, as I kind of mentioned, the differences in the rigidity of the test frames, if you're doing a test that's only controlled by the movement of the crosshead between two different test frames with very different rigidities, you may actually be imparting different effective strain rates on the sample. ASTM D638 for tensile testing only has instructions for constant rate of extension, which for a given sample size and sample length, again, should have the same strain rate, but in reality, there could be differences in the test frames and equipment. So ISO 527 has more extended instructions on performing strain rate control, and again, with the use of an extensometer with strain rate control testing, that you tend to get more repeatable results between different results that might be obtained between different types of test setups.
Oh, wow, that's really interesting. So do you see sort of a shift in the industry where we're moving from a crosshead controlled or a constant rate test to strain rate? Is that something that's becoming more common?
It is becoming more common. What's becoming more common is just kind of the proliferation of different options to do these tests, and as the test frames have gotten more advanced, they're able to more accurately control and sample these types of tests. So yes, it is becoming more common.
Great, thank you. So it looks like we've got one more question here, and it's related to temperature control. So it says, do you offer the ability to do low temperature testing for these methods?
Yes, we do. So all of these tests that I reported on, spoke about today, can be performed within a thermostatic chamber, either to do at elevated temperature or at below ambient temperature. Neither of the standards actually specify a required test temperature. They simply state that the test temperature should be reported with the results. So that is another factor, again, that should be considered and reported with what data that you're looking at. But just as with strain control, of course, plastics or properties can also be very dependent on temperature. So if you're wanting to collect the properties of a certain material at non-standard, non-ambient temperature, we have thermostatic chambers variety that can be used at a wide range of temperatures.
Oh, that's great. So I guess that the need for testing at elevated or lower temperatures would be dictated by the application of a particular material. Is that accurate?
Yep, that's exactly right.
Okay, wow, very interesting. All right, well, in the interest of time, I think it's about time to wrap things up. William, do you have any plans for any upcoming webinars that people can look out for?
Yes. We'll be planning another webinar on plastics to overlap with some of our other product lines. So we're planning one now to discuss some plastics applications with our thermal and spectroscopy instrumentation and how those might relate as well to mechanical properties. So keep an eye out for that next webinar.
Oh, that sounds fantastic. I'm looking forward to that. Well, William, I'd like to thank you for your time and for putting this excellent presentation together. I know it's going to be very helpful for a lot of people. With that, if you'd like to receive notifications about upcoming webinars and stay up to date on the latest developments from Shimadzu's testing products, please take a moment to fill out the survey and opt in for the notifications. Thank you for tuning in, and until next time, happy testing.